So from a practical point of view, say somebody gives you a graph and you want to know how hard is it to color it. Color it well, color it with as few colors as you possibly can. Well, we should start by acknowledging that this is hard. It's a hard problem. You can't necessarily find a really great algorithm to do that. I mean, there are algorithms, but they're not that great, you know? But on the other hand, we can ask, how well could you do, if you just try pretty hard? Like, how about if you don't really try at all and you just start coloring the vertices in, what kind of naive strategies could one try? Well, it's actually not as, dumb as you might imagine. Like, imagine the following algorithm, for example. We have some pot of colors, and we're trying to use as few as possible. So we start using the colors and we only pick a new one when we need it. And we color the vertices in the following way. We say, well, so this is kind of a recursive algorithm, right? So we say, are we done coloring? If we've been coloring for a while, if we're done, we're done. Otherwise, just grab some vertex that doesn't have a color yet. Well, that vertex has some bunch of neighbors, and some of those neighbors have been colored already. So what do? We just pick the first color on our list that is not in use by any of the neighbors of that vertex. And we use that color. And then we continue. We say, pick another vertex that we haven't colored yet. Look at its neighbors and use a color that we haven't used so far. Now, even though this is a kind of a naive algorithm, it does show us one thing, and that is that you never need more colors than one more than the maximum degree of a vertex. Let's take a look at this naive algorithm diagrammatically for a minute. So how do we color a graph? Now, first, let's just say that this algorithm you could also think of as a proof of the statement that you can always color a graph using at most capital delta of g+1 colors. So capital delta is the maximum degree of a vertex, remember. And how does the algorithm work? Well, we kind of start at some stage. We either haven't colored anything yet, or we're somewhere through the coloring, or maybe we're done. Maybe there are no vertices in the graph at all. I guess that's not a legal graph, but whatever. Okay. The first thing we ask is we say, are we done yet? Of course, in the beginning, the answer is going to be no. And as the answer is no, we proceed on to the kind of meat of the algorithm, which is we find an uncolored vertex, and we say, well, look at all of the neighbors of that vertex. There's at most delta of g of those neighbors, and we have delta of g+1 colors at our disposal. So what do? We just choose a color that we haven't already used on one of the neighbors. And well, you've used at most capital delta, so you can always find such a color. And then what do? We just color that vertex, okay? And after we've colored that vertex, we go back through the loop and we say, are we done coloring? If not, we color another one. And we can always keep doing that step because we always have enough colors to color one more vertex. Eventually, the number of vertices runs out, and we spit out the end, and we are left with a nice, good coloring of capital delta of g+1 colors at most. At this point, we have a couple different directions we could go. We have an algorithm now to color a graph. It kind of isn't that great, but it does something. It could be worse, right? And we can either ask, like, maybe can we do a bit better, or maybe can we actually just find an algorithm that gives us the right answer? Okay, so we'll look at kind of an algorithm that gives the right answer soon, but for the moment, let's just see if we can come up with a strategy that is maybe just a little bit more refined than what we just did. I mean, the thing that we just did, it doesn't give that nice a coloring, but maybe there's still an easy way to do somewhat better. So to see how to do just a little bit better, actually probably a lot better often with this algorithm, we realize that the tricky point is that if we have a vertex of really high degree that has all of its neighbors various different colors, then we're going to be forced to use a lot of colors to color that vertex. How do we try to avoid this situation? Maybe we can't, but we can try to avoid it by focusing on as much as possible, trying to color in vertices whose degree is as small as possible. From a practical point of view, what we're actually going to do is work backwards. We're going to find in our graph, we're going to look for a vertex of smallest possible degree. And what are we going to do? We're going to say that vertex is going to actually be colored in last. And we simply forget about it and realize that if that's the last vertex that we have to color, life won't be so bad because there aren't that many neighbors to have to worry about. So we forget about that vertex. We erase it, we erase all of the edges, and we say, okay, first I'm going to color in this graph without that vertex. And then after I'm done, I'll fill in that last vertex. How am I going to do the rest? Well, just the same way. You look at the vertex that is going to cause the least trouble, the smallest degree, and you say, that one I'll do second to last. And then you remove that. And that one I'll do third to last. Okay. You get an algorithm that works pretty well. We'll get nicer answers and we'll take a look. As a small observation, we're sacrificing a little bit in terms of like memory because we have to remember all this like sequence of steps and all that, but it's not, I mean, depending on how crazy your graph is, that's not such a bad thing. Okay, so let's take a look at that in a little more detail. Let's take a look at this smarter algorithm. So this is, I'm phrasing this as a recursive algorithm, and if you're not used to recursive algorithms, it can maybe feel like the sound of one hand clapping to some extent, but let's just get used to it. It's kind of fun. Here's how the argument goes. We start by saying, so somebody hands you this graph. You're going to use as few colors as possible, and we say, first step, does the graph have only one vertex? If so, we know what to do. Just give it some color, we're done. Okay, what if the graph has more than one vertex? Well, we choose the vertex of smallest possible degree in the graph. Maybe there's more than one, just pick one as small as possible degree. And now first, we color G minus V. We remove the vertex on all the incident edges, and we color that. Then we can then color V back in using at most degree of V plus 1, and degree of V is as small as possible, so that shouldn't be too bad. The only question is, how do we color the graph after we remove the vertex? Well, to color G minus V, we go back up and we say, well, does the graph have only one vertex? If yes, then we know how to color it, and then we go back to it, and if no, well, then we keep going. Okay, so let's take a look and see what this algorithm looks like in practice. Okay, so here I've drawn a graph. We're going to see how many colors we need to color this. This isn't necessarily going to be optimal, but we'll see at least what the smarter algorithm gives us. So we look at this graph and we say, where's the vertex of smallest possible degree? Or I guess the first thing we say is, does it have one vertex? Darn, it doesn't. It has more than one, so we have to start doing the algorithm. We say, okay, vertex of smallest degree is right here. It has degree 2. So we'll call that thing, let's call that thing V1. Okay. And so now what are we going to do? We're going to remove V1. So we're going to consider G minus V1. And the algorithm says, first, color G minus V1, and then go back to what you were doing. Okay, in G minus V1, it looks like all the vertices have degree 3. Yeah, all the vertices have degree 3, so it doesn't matter which one I pick. Maybe I'll pick this one will be V2. Okay, and so let me call this graph will be G1. And then I'll look at G minus V2. So I guess really, what do I say? Did G1 have one vertex? No, it didn't. I keep going. Okay. G2 is going to be G minus V2. It's going to look like a triangle. Okay. Now all the vertices have degree 2, so I pick one, call that V3. Now I let G3 be G minus V3. And that looks like this little dumbbell guy. And then I'm left with G4. Oh, that's G3, sorry. G3 is G minus V3, right? Then I'm left with G4. This was V4, is G3 minus V4. And that's just a single vertex. And finally, we know how to color it. So we say, okay, I'll color it. And that means that in the previous graph, I knew that's the color I give it. And I say, okay, now how was I supposed to have colored G3? The algorithm said to color G3 You remove the thing, you color it, and then you stick in a color on V4. V4 has very small degree, only degree 1. We'll just stick some other color there. Now, these are colored in our prior graph. So we have our, I'm not sure which one is which, but it doesn't really matter. We have our two vertices here. V3, we know we need a different color to color. It's adjacent to those two. So I give it a green color. Now I've colored my, I've colored this triangle that I'll draw down here. I've colored this triangle really, I mean, I've colored this picture all the way up through these graphs. I could color them all at the same time, maybe I should. So let me go ahead and do that, you know. Choosing that color down below really chooses what it's going to be for all those graphs up above. Okay. And now I say, okay, V2 had minimal possible degree, but it still had a lot of degree. It has degree 3. Pick some color for it. Boom, blue. This one is blue. And now V1 has degree 2. And so I can just choose some color that that I haven't used adjacent to it. And this is the kind of the only interesting step there. What was that? What have I done? I've come up with a 4 coloring of this. So this is now 4 colorable is what we found. This is better than the other algorithm would have given because the maximum degree of a vertex was 4, and so the other thing would have only told us that we're bounded by at most 5. So we did a little bit better than we could have, and that's how this algorithm works. I suppose it's worth mentioning that in that last graph, both of the algorithms would have actually given us the same answer. But in general, when you're looking at more interesting and complicated graphs, that second algorithm typically does a lot better than the first one. You know, it's good to take a look at how sensitive these algorithms are to the choices that we make. So let's take a look at 2 different ways we could have run the naive algorithm. So here's a graph that I've drawn. As you can see, I've colored it with a 3 coloring. I've called my colors A, B, and C. And you can see that this is a totally legitimate, I hope it's legitimate. Yeah, it looks good. Yes, it's a good, nice, proper 3 coloring of this graph. Let's see how I could have, I mean, you could have gotten a 3 coloring on this graph if we'd used the naive algorithm. Like, for example, I could have said, let me first do this vertex here. I'll give it a color A. Then I'll do this vertex here. I'll give it a B. I'll do this vertex here. I'll give it a C. In the naive algorithm, all you have to do is just pick some vertex each time and give it some color that's unused. You might like order your colors and say, use the first unused color that arises around a given vertex. That's one way to do it. Next, let me do this vertex right here. The first unused color is A, so I'll just stick an A there. Now I'll do this one over here. I haven't used a B around there, and maybe I'll do this one here. That could be an A, make that an A. So that's adjacent to this guy and to this guy, but so I can use an A. And now this guy right here, I can use a B. And I've done a nice, just fine 3 coloring. But let's do a different set of choices now. I'll start the same way. I'll do an A, I'll do a B, and I'll do a C. But now last time I did this vertex first. This time I'm going to do this vertex first. So I'll give this an A. And now what do I find over here? Over here, this vertex is adjacent to an A, a B, and a C. Trouble, trouble, trouble. We are forced already to use a new color. We have to use color D. And so we immediately have just failed with this algorithm to find a 3 coloring, even though we knew that one exists. And now I can finish this off and get something. I'll make this a C, the next available color there, and I can make this an A. That we got into 4 coloring, but we didn't get as well as we could have. It could have been a lot worse, I guess, if you think about it. This vertex over here has degree 5. Maybe we would have been forced to do a 6 coloring if we'd been really dumb. Actually, I don't think that can happen here, but you see the point. It's a little bit sensitive to how we make our choices. It doesn't come in nearly as bad as it could, but the cleverer algorithm typically does a bit better. Anyways, this is just one example.